Question says both diagonals of a convex quadrilateral have length 1 unit and the diagonals meet at 45 degrees angle. What is the difference between the largest and the smallest possible areas of such a quadrilateral? Okay, now let's just draw this quadrilateral so that we can have an imagination. Assuming that's my convex quadrilateral. Remember, convex quadrilateral is just a quadrilateral whereby all angles or all interior angles are less than 180. Okay, so we've been told that diagonals meet at 45 degrees, so that's 45 vertically opposite, that's 45. Because of angles on a straight line, that's 135 and that is 135. Okay, so I'm going to call this part here that's from this vertex to where the diagonals meet, just this length here. I'm going to call this one A, going to call this one B, this one C, and this one D. Okay, now I'm going to say this is triangle 1, that's triangle 2, that's triangle 3, that's triangle 4. So let's evaluate the area of all the 4 triangles. The area of the whole quadrilateral will be area of triangle 1, which is half A multiplied by B multiplied by sine 135, plus area of triangle 2, which is half B multiplied by C multiplied by sine of 45, plus triangle 3, which is half multiplied by C multiplied by D multiplied by sine 135, and we add triangle 4, which is half multiplied by A multiplied by D multiplied by sine 45. Okay, it's important to remember that sine 45 is actually equals to sine of 135, because you can always reduce sine 135. If we reduce sine 135, we get sine of 180 minus 45, and 180 minus 45 is in the second quadrant where sine is positive, and that simplifies to sine 45. Okay, just a reminder there. Okay, now we know that sine 45 is equals to sine 35. Means we can take out half sine 45 as our highest common factor, and we are left with AB plus BC plus CD plus AD. Okay, so let's simplify this further. This is equals to a half multiplied by 1 over root 2, that's sine 45 special angle 1 over root 2. Now here we will group. Here we can see these two terms have a common factor of B. These two terms have a common factor of D, so let's factorize that. So we take out a common factor of B and we are left with A plus C. Take out a common factor of D, we are left with C plus A. Okay, now we have a common bracket of A plus C, A plus C. So this simplifies further into 1 over 2 root 2 into A plus C and B plus D. Okay, but going back to our diagram, A plus C is actually this diagonal here. Okay, so A plus C, we can replace this with 1 because we are being told that the diagonals are equal to 1. So A plus C is 1, B plus D is also 1. So the answer here is just equal to 1 over 2 root 2. Okay, now looking at this answer here, we can see, or we can conclude that the area of this quadrilateral does not depend on how the diagonals cut each other, because 1 over 2 root 2, it is the minimum or the maximum area, meaning the difference between the minimum and the maximum, or maximum minus minimum, is equals to 0. Now, next question says, the diagram shows three squares such that the vertices of the inner squares are positioned a quarter of the length along the sides they touch. So, for example, AB here will be a quarter of AC, and BD will be a quarter of BE. Okay, so if the area of the largest square is 64 centimeters squared, find the area of the smallest square in centimeters squared. Now, we know that AC squared is equals to 64. Okay, because AC squared is basically the area of the bigger square. So side AC is therefore equal to 8 centimeters. Right? So if AC is equals to 8 centimeters, that just means that BE, which is also equals to CE, is equals to 2 centimeters, and BC will then be equals to 6 centimeters. Okay, now we are going to look at this right angle triangle here and use Pythagoras to find the length of BE, which is a side of the second square. Okay, so from Pythagoras, BE squared will be equals to 2 squared plus 6 squared, and BE squared will be equals to 4 plus 36, which is 40 centimeter squared. Okay, now remember that BE squared is also the area of the second square. Okay, because a square is a side squared, so the area of this second square is 40 centimeters squared. Okay, now that means that we can say the ratio of proportion between the areas here is 64 divided by, not 64 divided by, but 40 divided by 64. Because if we multiply this by 64, then we get the area of the second square. Okay, so that means the area of the third square, so write it here, so area of third square will then be equal to 40 divided by 64 multiplied by area of the second square, which is 40. Okay, this is true because if we wanted the area of the second square, area of second square, we would have said 40 divided by 64 multiplied by 64, and this was going to give us 40 square centimeters. So we use the same proportion to find the area of the third square. So this will be equal to 40 times 40 is 1,600 divided by 64. Simplify that further. I'm just going to write 1,600 as 16 multiplied by 100. And I'm going to write 64 as 8 times 8 just to make calculations easier. So 8 goes in there once, and it goes into 16 2 times. So we end up with 200 divided by 8, which is equals to 25 square centimeters as the area of the third triangle. Of course, if you wanted to, you could have continued with these calculations. After you find 40, you take the square root of 40, then it was just going to be a little longer. But of course, if you wanted to do that, you are more than welcome. But what we're teaching you here is for you to see patterns, to see trends, to see the easier way of doing things. Okay. This question says triangle PQR is inscribed in a square of side 1. Prove that area of PQR is less than or equal to a half. Okay, now I'm going to shade this triangle here. and we are going to calculate the area of the unshaded part and subtract it from 1 and see what we are going to get. Now, I'm going to call this little piece here A, this one B. That makes this 1 minus B, makes that 1 minus A. I'm going to say that is C, and that is 1 minus C. Okay, so that's my triangle 1, triangle 2. This other shape here, shape 3, is a trapezium. Now, area of unshaded would be equals to area of triangle 1 is just going to be half base of C and a perpendicular height of 1 minus A, plus area of triangle 2, which is half A times B, plus area of this trapezium number 3 there is half sum of parallel sides multiplied by perpendicular height, which is just the side of a square for 1. So let's try to simplify this further. Now we get a half C minus half AC plus half AB plus half minus half B plus another half minus half C. Okay, so you can see that this term here cancels out with that term there, and we have a half and half, which will give us 1. Let's just write 1 in the beginning there, minus 1 over 2 AC plus 1 over 2 AB minus 1 over 2B. Okay, so we can simplify this further if we want to. This is 1 minus a common factor of a half into AC plus AB minus B. So that's the area of the unshaded part. So area of triangle PQR will just be 1 minus the area of the unshaded part. So that's 1 minus a half. Let me make this square brackets. Half into AC plus AB minus B. Okay, if we simplify this further, we get half into AC plus AB minus B. Now from here, if we refer back to our sketch, it's very important that you remember that A is less than or equal to 1. B is also less or equals to 1. The same with C. It's less than or equals to 1. That means the maximum value that all A, B, or C can take is 1. So let's just write that down so that we don't forget. Now, A is less than or equals to 1. B is also less than or equal to 1. C is also less than or equals to 1. Okay, the question says prove that the area is less than or equal to half. So let's substitute the maximum possible values for all A, B, and C in our expression for the area of PQR there. So we know that maximum possible value of A, C, and B is 1. So this will be 1 plus 1 minus 1, which is just equal to a half. So what this means is that our area of triangle PQR is actually less than or equal to a half. Okay, it can't be more than a half because we've just substituted our maximum possible length of A, B, and C, and it's equals to a half. So this area will always be less than or equal to a half. This question says, a 10 centimeter by 6 centimeter rectangle above, or in this case on the side, is divided into 5 smaller rectangles of 2 centimeter by 6 centimeters. Diagonal AB is drawn, as well as a number of smaller diagonals, as shown in the figure. How much larger is the shaded area than the unshaded area? Okay, so we know that these smaller rectangles have all bases of 2's, which adds up to 10. But very important information here is that since all these rectangles are equal, if I construct lines like that are perpendicular to the height of this rectangle, they will all have the same width. Okay, since all these rectangles are equal, that means the distance from here to here is equal to the distance from here to here. All these are equidistant because all these rectangles here are equal, so they will divide that height into 5 equal parts. Okay, so I'm going to call this one here h. Okay, and just to remember that h is actually 6/5 because we divided a height of 6. Remember, this whole thing here is 6. Divide the height of 6 into 5 equal parts. So the distance here, or the height at that point, is 2h. At that point there is 3h. At that point is 4h. And at the top there is 5h. Okay, and h is 6/5 because that height is 6 centimeters. Okay, so from here you actually have most of the information that you need. Another thing to note that's very important is that this triangle 1 is equal to that triangle there. Okay, this number 2 is equal to this one here. Number 3 is equal to this one here. Number 4 is equal to that one there. And this triangle number 5 is equal to that one there, because they are constructed in a similar fashion basically. Okay, so now let's go ahead and evaluate the area of all these shaded triangles. So the area of, use black, area of the shaded triangles will be equals to 2 multiplied by, this 2 is for the fact that every triangle has a partner, so there's 2 times every triangle here. So multiplied by half is from the formula of the triangle, half base times perpendicular height, and multiplied by 2 because all of these triangles have base 2. The only thing that's different is the height. Okay, so the height of the first triangle is h, second triangle is 2h, 3h, 4h, then 5h. Okay, so if we simplify this, these 2 cancels that 2, and we have 2 into h plus 2h, that's 3h, 6h, 10h, then 15h. Okay, and which this is equals to 30h, but we know the value of h already is 6/5, so this will be equals to 30 multiplied by 6/5. 5 goes in there once, goes in there 6 times, and we have 36 square centimeter for the area of all these shaded triangles. Okay, now the question says how much larger is the shaded than the unshaded. Now we need to find the area of the unshaded. Okay, so the area of this whole rectangle is equals to 10 multiplied by 6, length of 10, height of 6, or length of 10, width of 6, and this is 60 square centimeters. That means the area of the unshaded will be equals to the area of the rectangle minus the area of the shaded, and we get an answer of 24 square centimeters. Okay, so the difference now will be equals to area of the shaded is 36 minus the area of unshaded, which is 24, and we get an answer of 12 square centimeters, which means that the shaded area is 12 square centimeters larger than the unshaded area. Okay, hope that makes sense. Okay, now this question says side BC of ABC is 192 root 6. So that's BC, this side here. Inside the triangle, a line segment DE is drawn parallel to BC, forming trapezium DBCE with the area 1/3 that of ABC. What is the length of DE? Okay, now they told us that this is parallel to that, and this has a third, 1/3 of ABC. There's the area of this trapezium here, which automatically makes this 2/3 of, so 2/3 of ABC. Okay, now from here we know that if a triangle has two parallel lines like that, then that means ADE is actually similar to ABC. Okay, so that's the conclusion we can make. Now let's start there. So triangle ADE is similar to triangle ABC. Okay, and when two triangles are similar, what do we know? That means that AD divided by AB is equals to DE divided by BC, which is equals to AE divided by AC. So I'm going to say this is actually equals to K. So I'm just going to call this proportionality between two similar triangle, or proportionality between two sides of triangles that are similar, equals to K. Now, just to show you something, I'm just going to take this blue part here and multiply both sides by K. Multiplying both sides by K, I mean this. This will use this as K because that's also equals to K. Now we get AD multiplied by AE divided by AB multiplied by AC, which is equals to DE multiplied by AE divided by BC multiplied by AC. And this is equals to K squared, because basically what we did was just multiply both sides by K. Okay, now let's stop there for a moment. We'll come back to that. If I take the area of ABC from two similar triangles here, the area of ADE, and I divide the area of ADE by the area of ABC, what do you think will happen? Let's just find out. Now, I'm going to take area of triangle ADE and divide it by area of triangle ABC. Okay, so let's do that. Now, using the area rule, I know that the area of ADE, if I call the angle A there theta, it will be half multiplied by AD multiplied by AE multiplied by sine of theta. That will be divided by half AB multiplied by AC multiplied by sine theta. So from here, half cancels the half, sine theta cancels sine theta, and we are left with AD multiplied by AE divided by AB multiplied by AC. But look at what happens. So this here is the same as that there. Okay, so that means if I take the area of, or if I take the ratio rather of the areas of two triangles that are similar, the answer that I'm going to get is k squared, meaning the proportionality of the sides squared. Okay, so we are going to use this philosophy here to solve this problem here. Okay, so if we take from this problem here, if we take the area of triangle ADE and we divide it by the area of triangle ABC, what do we get? This is equal to, we know now that ADE, actually the area of ADE is 2/3 of the area of ABC. So let's substitute that in. So now area of ADE is 2/3 of the area of ABC. And this is just divided by the area of ABC. Okay, so that can cancel that, and that means our k squared is actually equals to 2/3. Okay, which makes the proportion between sides of these two similar triangles being the square root of 2/3. Okay, now from the question they gave us side DE, no, they want side DE, sorry, but they gave us the length of side BC. Okay, we can see that we can say DE over BC because these two sides are in corresponding with each other, okay, from the two triangles. Now, if we take side DE divided by side BC, we should get the square root of 2/3. Okay, but we do have BC as 192√6. So DE divided by 192√6 will be equals to the square root of 2/3. And therefore, DE will be equals to 192√6 multiplied by square root of 2/3, which we can simplify this further into 192 multiplied by the square root of 6 times 2/3, which we get 192 multiplied by square root of 4, because 6 times 2 is 12, divided by 3 is 4. So we have 192 times 2, which our side DE at the end is equals to 384. Okay, so it's very important to remember that if you take the ratio of the areas of two similar triangles, what you actually got is the proportionality constant between the sides of those two triangles squared.